think we were just discussing the last part of this chart. Squeeze film lubrication. So squeeze film lubrication is an effect which exists in most of the bearings. So this is basically an effect by which the lubricant, when trapped between two surfaces, is unable to move out or squeeze out during a reciprocation motion. So when the two surfaces are coming together, okay, so in this case, because of the movement of one surface closer to the next surface, the gap here will be reduced and the liquid will get squeezed out, so therefore there can be a dry state here, and this kind of dry state will not be good because it will lead to adhesion, immediate adhesion between metal surfaces, and there will be wear, adhesive wear. So but if we select the lubricant of sufficient viscosity, then the viscosity ensures that the lubricant will not be able to get out of this contact immediately. So there will be enough time during which the motion of this will reverse. So since it is in reciprocation, it can be because of vibration or it can be part of the design. So squeeze film action is always present in most of the bearings. So basically squeeze film helps in damping and it will prevent unnecessary adhesive wear or adhesion. And the last one here listed is hydrostatic lubrication. So hydrostatic is basically pressurized. So for example, if we have two surfaces together here and then we introduce liquid or gas at high pressure, so you will have to introduce from many entrances. So because of this high pressure, the shaft part, which is carrying the load, will be lifted and it will be actually on the the load will be taken by the high pressure of the fluid. So this is applicable for both liquid as well as for air. So many of the air bearings actually run on this. So air bearings will run on this principle. That means you have to have a source of high pressure air in order to run this bearing. So you should not run the bearing unless the pressure has been increased or the system has been pressurized.
Excuse me, sir.
Yes.
Sir, saying that a squeeze phase lubrication is like, sir, in every surface there are irregularity in surfaces.
Yes.
So, sir, lubricant also present there.
Yes.
Which helps to don't mix adhesion bond between the surfaces. So in general, we can say that, sir, every lubrication has a squeeze film lubrication.
Not every lubricant will have sufficient to for our engineering system. So the viscosity is very important. If the viscosity is low, then they will get squeezed out and there will be dry contact. So for example, this is one reason why we cannot use water as a lubricant, because water has very low viscosity and it will squeeze out. Of course, there are some other properties of the lubricant that also helps. just like we were talking about boundary lubrication and so on. So just presence of any liquid will not help, so it has to have sufficient viscosity to have this squeeze film lubrication effect. That means because of the squeeze film lubrication, the load will be carried by the lubricant, the highly pressurized lubricant exists between the two. So this is just shows the engine, piston and the crankshaft arrangement. So here you can see that it's full of tribological systems here in this case. So the piston ring sliding against the cylinder liner here, and here there are so many journal bearings between this crankshaft and the piston rod. And for the lubrication part, actually they experience all of these lubrication at one point or the other. So for example, from boundary lubrication to mixed to hydrodynamic to elasto-hydrodynamic. So all kinds of lubrication regimes, as they are called, exist in this case. So dry sliding we will just skip now at the moment, because we have talked quite a lot about dry sliding part. So in dry sliding, the important part is the material selection. So materials should be selected which has got good tribological properties. Coupled with the bulk strength. But often the case is that a material which has got good tribological properties will not have sufficient bulk strength, bulk properties. That is a normal case. So therefore we have to find a way to apply those materials. So one of the method is to apply them as coatings. In the case of coating, you do not rely on the bulk property, but you only utilize the tribological property of the material. For every tribological system, solid lubrication should be the first choice. So there are many types of solid lubrication, and nowadays the solid lubricants are used for almost all cases, even for journal bearings, and even for rolling element bearings. The solid lubrication is used in the form of some coatings. So choice of the load bearing pair materials, so which has got intrinsic friction property, low friction property or required friction property. Application of composites. So composites are very useful materials because they combine both good tribological properties with good bulk property. So therefore composites should be used, and many times composites are made with solid lubricants inside them. So for example, PTFE is a solid lubricant, so I can add PTFE particles inside a polymer or even inside a metal. So some metals are made into a kind of spongy metals which has got holes inside, and those holes can be filled with PTFE. Then application of surface treatments is also very important depending upon the situation. If low friction is not a requirement, if our concern is only wear, then hard coatings are applied or hard surface treatments, which is also known as hardening or surface hardening. So surface hardening is applied on the surface, and this is very common. For example, gear surfaces, the bearings, all surfaces are surface treated for high hardness. Then application of coatings. Coatings are very special case because it is very important that we select the coating appropriately, because the coating may delaminate and that will cause more harm than good. So whether we are selecting a hard coating or soft coating, we should be very careful about that. A hard coating, if delaminated, can lead to more wear. A soft coating, even if it gets delaminated, it is still helping in the lubrication process. So in general, soft coating is applied for friction reduction. So whenever there is friction reduction need, like soft coating of PTFE, or generally PTFE is the best choice, or Babbitt material is also a soft coating. Hard coating will be, as I said, some oxides like or carbides. Silicon carbide is one good example, silicon carbide coating. So these are hard coatings are applied often on tool materials, because with the tool materials our main concern is to reduce wear, and of course friction is also, we want to reduce friction, but wear is one of the most important criteria. Another important thing in lubrication study is known as Stribeck diagram. Here the coefficient of friction, as you can see, it varies from 0.001, which is the usual case for normal journal bearings in the hydrodynamic lubrication regime, to 0.1 or even higher. And this x-axis, we have got this Hershey number, viscosity multiplied by the RPM divided by the pressure or the load, whichever. This is named after Hershey, but sometimes this number is also known as Sommerfeld number. So in the books you will find sometimes written as Sommerfeld number or Hershey number. So when the viscosity is high and RPM is high, speed is high, that means we are in this range, and the load is low. So as we move into this direction, we have low coefficient of friction here, and this is the hydrodynamic lubrication regime. It can continue for some time, or after some times it might start increasing, depending upon the situation, depending upon the lubricant, because it depends upon the thermal properties of the lubricant. Mixed lubrication is in between boundary and hydrodynamic lubrication. So here basically you have got partial hydrodynamic lubrication. So for example, you may have some hydrodynamic lubrication on some of the asperities, while other asperities have dry contacts. And EHL happens when there is some elastic deformation. So for example, if I've got two surfaces like this under very high heavy load, then because of elastic deformation, these two surfaces will deform slightly. This will be elastic deformation. So this elastic deformation allows the thickness of the lubricant to be sufficient here so that lubrication can happen. So this is known as EHL, or elasto-hydrodynamic lubrication. So this can happen at very high load, with materials like steel, or it can happen for softer materials like rubber or plastics, because they have lower value of elastic modulus and they will deform at lower load. So when you are dealing with rubber and plastics, you can be in the EHL regime, and when you are dealing with steel, normally at high load, then again you can be in the EHL regime. So EHL regime is very prevalent, and this helps in the lubrication process. So this Stribeck curve can also be given in terms of H over sigma, where H is the film thickness and sigma is the standard deviation of the asperity heights. This is also known as composite roughness. So as H over sigma increases, you go from boundary to hydrodynamic lubrication. So for example, H over sigma is less than 1 in the boundary lubrication. It is in the range of 1 to 4 in the mixed lubrication, and in EHL it will be more than 5, and again it continues, so more than 5. So that means you have got sufficient film thickness here. So film thickness is at least 5 times the composite roughness. So in that case, the hydrodynamic lubrication works very perfectly. Again, here we have got a schematic diagram of the engine parts, and I think the last time in the lab you were asking about how the lubricant circulates. So basically the lubricant is supplied through a channel and they are sprayed here. So lot of lubricants will be sprayed here. So we cannot see inside a running engine, but this is the principle. So the lubricant will be sprayed from some directions here, and these lubricants will be picked up by the piston ring, and that is how it will lubricate the piston and the cylinder liner. And these lubricants will fall onto these surfaces, these journal bearings, where they will lubricate the crankshaft. Similarly, some of the lubricants will also fall onto here in the camshaft, so where cam and followers have high friction, so here also it will lubricate, and the lubricants will drip down, and finally at the bottom you have got a sump. And the lubricant will get collected into the sump, and from here it will be filtered, and then again it will be supplied back again. So this is how the circulation of the lubricant takes place in our IC engines. So just now I was talking about this ratio, which is known as lambda, effective film thickness divided by the surface roughness. So this is the composite roughness, that means roughness of the two surfaces together. And in general, we can see that from 0 to 5 and beyond 5, it is good lubrication. And in the case of piston ring and cylinder liner, we have got starting from boundary to hydrodynamic lubrication. So all kinds of regimes will operate. For cam follower, mostly boundary and mixed lubrication. and the other journal bearings of the engines, hydrodynamic lubrication will generally follow. So this is a very complex situation for engines where we have got all kinds of lubrication regimes. So common types of bearings. We have been talking about the lubrication, and basically each lubrication type is the bearings are based on each lubrication type. So for example, if we talk about the fluid film bearings, then there are journal bearings, thrust bearings, squeeze film, mostly squeeze film effect, okay, and hydrostatic bearing. The dry bearings will be just solid lubrication. Semi-lubricated bearings will be the porous metal or in situ lubrication. Or in situ lubricated polymers we can use. That means polymers impregnated with liquid lubricants. And finally we have got rolling element bearings, so ball bearings, roller bearings, and so on. So these are the main types of bearings which operates in all the engineering systems. Some of the merits of fluid film bearings over rolling element bearing: unlimited fatigue life. So rolling element bearings suffer from the fatigue loss, fatigue wear, or fatigue failure because, as you know, the stresses are changing quite dramatically because of the non-conformal contact. Whereas in the fluid film bearings, generally the contacts are conformal, and therefore load is uniform and less changing. So fatigue life is almost unlimited here. Minimum space requirement. So space requirement is really very small, just based on the thickness of the lubricant you have. So this is the one of the good point of fluid film bearing. Good damping property. So damping is also another property of the lubricant. So because of the presence of fluid film, the damping will operate. So if the gap here is filled with liquid, so any vibration from the system will get absorbed here, because this is a viscous fluid, and as you know, the viscous fluid will provide damping property, which also means low noise and low cost because it's very simple. Merits of rolling element bearing over fluid film bearing are generally low starting friction. So this is the most important part of rolling element bearing, is low starting friction. For fluid film bearing, the starting friction can be very high, in the range of 0.2, but here it will start with very low coefficient of friction, just like 0.001. Can support radial and axial loads. So that means one single rolling element bearing can support both radial and axial loads, which is not possible in the case of fluid film bearing. So you will need a thrust bearing and a journal bearing to take care of the axial load and the radial load. Can withstand lubricant starvation. So in machines, often there will be a situation when the lubricant will dry out, and in that situation the rolling element bearing will perform better, because the low friction is because of rolling, and therefore it helps. Free from low temperature starting issue. So for most of the lubricant, the viscosity goes down. The viscosity increases as temperature goes down. So as temperature goes down, the viscosity increases, and high viscosity means high coefficient of friction. So this is the problem with fluid film bearings, but in the case of rolling element bearings, we do not have this problem, so free from low temperature starting issue. No need to re-lubricate and lubricant well sealed inside. For fluid film bearing, in many cases re-lubrication is necessary, and in most of the cases lubricant supply is a supply line is necessary, so there must be a supply of the lubricant. Whereas in the case of rolling element bearing, no need to re-lubricate. All you need is a good sealing, so that the grease or the lubricant stays inside the bearing and doesn't come out. So here we have a comparison of different types of bearings as far as their performance is concerned. So in general, we take fluid film bearings, the dry bearings, partially lubricated or starved bearings, and rolling element bearings. So the start of friction, as you start the machine, for the fluid film bearing, the start of friction is very high, 0.25, and that's because it takes some time before the shearing can happen. So most of the lubricant will be in a bit of viscous state, or it can also be sometimes it can also be starved in some cases. So for example, the lubricant may not be fully distributed all over, because it takes some rotation before it starts. And the another is the hydrodynamic lubrication will not act unless the speed has achieved some range. So in the beginning it will be boundary lubrication and therefore high friction. Dry bearings, of course, does not work on hydrodynamic lubrication, so it will start with high friction, 0.15. Partially lubricated, also high friction, 0.1. But rolling element bearings starts with very low coefficient of friction, 0.002. So this is the best advantage of rolling element bearing. And then running coefficient of friction is low for journal bearings or fluid film bearings, is still high in the range of 0.1. So dry bearing cannot go very low coefficient of friction because they do not have lubricants, rather they are working on the solid lubrication principle. Partially lubricated may go up to 0.005, but the rolling element bearings can also achieve 0.001, similar to the journal bearings. With regards to velocity limits, fluid film bearings have got very high velocity limits, so they can operate at very high speed limits, which is not true with other bearings. The rolling element bearings can also run at medium speed. Load limits, also very high load limits, and here also very high load limits. Life, fluid film bearings has unlimited life because the fatigue life is very high, whereas rolling element bearing has low life because of the fatigue problem. So you will often see that the rolling element bearings often fails because of the fatigue problem. Lubrication needs, fluid film bearing has got high lubrication need, whereas rolling element has got low. high temperature limits depends on the lubricant method or the lubricant themselves. This one is material dependent, this one also lubricant dependent, and this is also lubricant dependent. Low temperature limits also depends on the lubricant. These two don't have this issue, and rolling element bearing also may have low temperature issues related to the lubricant used. The vacuum not applicable. We cannot apply fluid film bearing for vacuum application. Dry bearing is excellent for vacuum application. Partially lubricated also can be used in vacuum, and rolling element bearing can also be used in vacuum depending upon the lubricant we are using. Again, there are some greases which are available for vacuum application. So in that case, you will have to use those greases for vacuum application. Noise, this one has got very low noise, whereas rolling element bearing has got high noise. Dirt and dust tolerance, in these two we need seals so that no dust will go inside, and as we know that if dust goes inside, the bearings will fail very quickly, very soon. Radial space need very small, because we need a very small space just for the lubricant, whereas this one is very large because here we have got rolling elements, so we have to accommodate the balls or rollers inside. So here we have got filled with rolling element all along, so we need this much of a space for the rolling element bearing here. Damping capacity very high, and this is medium, and the cost of fluid film bearings can be very high, depending upon the type of bearings, and this one is medium, and these two are good in the sense they are very cheap, and often many times people are trying to use dry bearings or partially lubricated bearings for this reason. So this is a chart which can be used to decide which bearing we should use, whether we should go for rolling element bearing or we should go for fluid film bearing. So here you see the x-axis. On x-axis you have frequency of rotation, or the rotation in RPM or RPS. So for example, if we work in RPM here, so 1000 RPM, and this is 10,000 RPM and 100,000 RPM. And in terms of load in Newton here, so this is the load. So for example, if we say that we fix the speed at this range of RPM and increase the load requirements for the bearing, then we can see how it will go from one type of bearing to another. So in the beginning, at lower load, we can work with rubbing bearings, which are basically dry bearings. As we go up in the load, for the same speed, we will need rolling element bearing, and beyond here, so beyond this value of load, we will need fluid film bearings here. So this is the way we can select which type of bearing we should use. And here we have got shaft diameter in meter, or within brackets in inch. So here you can see the shaft diameter given in 0.125, 0.25, and so on. In a similar way, if we fix the load, for example here, and increase the speed, RPM, and we can see that how the requirements will increase. So as we increase the speed, we can go from dry bearing to rolling element bearing and to again journal bearings or hydrodynamic lubricated bearings. So in both cases, as we make the contact more and more severe in terms of either in terms of load or in terms of the speed, we will need fluid film bearing. So this is the general concept, and this is how we can decide which bearing we should be using for our application. There are some more qualitative comparisons of the journal bearings or the rotating comparison of journal bearings with the rolling element bearing. So accuracy of radial location. So obviously in the fluid film bearing it will be excellent, whereas in rolling element bearing it is good. So this is the accuracy in the radial direction. And axial load capacity, it will have none, so you need a thrust bearing to take the axial load, whereas in the case of rolling element bearing it can take both radial as well as axial loads simultaneously. Low starting torque, it has excellent, and this is also excellent. High temperature performance, limited by lubricant. This is also limited by lubricant and the materials we used. Lubricating system requirements. The fluid film bearing can be very, very complex, whereas this one is relatively simple. Tolerance of dirt, sealing and filtering essential. Good sealing is important. So in the case of dirt, both types of bearings cannot tolerate dirts, so it is very important to have very good sealing, and in the case of fluid film bearing it is very important to have the filtration going on. So important requirements to be considered for bearing selection. So these are the important things which we need to consider while selecting the bearing. The first thing is that typical engine losses at partial load can go up to 10%. So 10% is the mechanical loss. But of course other losses are also there, for example brake output and other thermal losses, but this is purely the frictional losses here in the engine. And at full load the frictional losses can be reduced. And another thing we should know that the engine generates power to overcome friction of the vehicle. So there are many other types of bearings, other places where you have got lot of friction. So, for example, friction between the tire and the road. So all those losses are also basically borne by the engine. The engine has to generate that much power to overcome those frictional losses. So the final decision on bearing selection depends on the mechanical requirements, environmental requirements, and the economics or the cost. So percentage of energy is lost as frictional losses in automobiles. So this is about 10%. Important consideration for a bearing is the low starting and running friction. So we want low starting friction and low running friction. Frictional heat is the consequence of power loss, which places limit on the type of bearing, load, and speed. And the coefficient of friction which is necessary for us is in this range 0.001 to 0.002. for running machine in rolling element or fluid film bearing. Another is about the speed. The speed limits, surface speed limits the selection of the bearing. For example, surface speed of 1600 to 3100 meter per minute is the limit for ball bearings. And for fluid film bearings, the surface speed can go up to 8700 meter per minute. So the speed limit for rolling element bearing is also calculated by this equation, where it is written as dn. Dn is the limit, where d is the bore diameter in millimeter. And n is the speed in RPM. So dn in the range of 5 into 10 to the power 5 to 10 into 10 to the power 5. So this is the limit for the rolling element bearing. So by calculating the dn value, we can find out whether we are within the rolling element bearing range or not. If the range has gone beyond this, then we should use the fluid film bearings. So this dn number can be used. Then load, in general, both fluid film and rolling element bearings can take high load up to their fatigue limits. Extremely large loads, such as for observatory dome, telescopes, etc., the mass of 100 to 450 tons can be supported by hydrostatic bearings. So for extremely large load, we cannot use any other bearing but hydrostatic bearings. And the example is for telescopes. So telescopes tend to be, the mass of the telescope tends to be in the range of 100 to 450 tons, and they are supported on hydrostatic bearings, which are externally pressurized oils. Shock load, rotor unbalanced load, and cyclic loads, and the combined radial and thrust loads should also be taken by the bearings. So these are also other requirements of the bearings.
Sir, here a speed, which that means which surface we are talking, which speed? Because for selection of bearing, we don't know which type of bearing it is. So which speed we are talking about? The surface of what, of which?
So it can be the surface speed, that means if the shaft is rotating at some RPM, right? So there will be some surface speed, right?
Yes.
So this surface speed we can calculate based on the RPM. So that will be the surface speed we need to know to decide about ball bearing, or we should go for fluid film bearings.
But sir, I think in thrust bearing there is no such type of surface.
In thrust bearing also you have got the surface speed, because so thrust bearing is basically axial load here, and it is rotating. So because of this rotation, again there will be hydrodynamic lubrication acting here. So here also there is some surface speed here, because without this rotation you will not get the hydrodynamic action here.
Yes.
So in thrust bearing also you need to have some surface speed. Now something related to speed and load is known as PV diagram, or also known as PVT diagram. So PV diagram is basically pressure velocity diagram, and T is the temperature part. But if we fix the temperature as, let's say, room temperature at 25 degree or any temperature, then it is known as PV diagram. So here basically log of P and log of V is plotted, and it gives us an envelope here. That means our bearing can work within this envelope range, leaving behind this part, two extremes. So the load and the velocities must be within this envelope. So this is known as PV diagram, and for each bearing actually people try to find out the PV diagram so that we can find out the limits. That means if you are increasing the load, then the velocity will go down. We cannot use at very high speed here as we increase the load, and the vice versa. So here you can see that this kind of PV diagrams have been given for many non-metallic bearing materials. So often for solid lubricants or dry bearings, we can see this kind of PV diagrams. But PV diagram can also be produced for lubricated bearings as well. So PV diagram can be created both based on the friction requirement as well as based on the wear requirement. So in the friction requirement, you will vary, for example, at a fixed velocity you will vary the load, you will increase the load until you get a kind of friction coefficient within your range. Or if it is wear requirement, then you will, at a fixed velocity, you will vary the load, increase the load, and as long as you get a given wear coefficient. So in the wear requirement you will measure wear, whereas in friction requirement you will measure friction, and you will fix one and vary the other. So either you fix the speed and vary the load, or you fix the load and vary the speed. And basically you will try to find out a region within which your requirements are satisfied as far as friction or wear is concerned. So in the case of dry bearings, the idea is that we should get materials with PV limit as high as possible. So here you can see that polyimides has got 4. Thermosetting polyimides filled with some other materials. So generally polymer composites tend to give us high PV limits. Nylon or acetal will give you lower PV limits because they are not very stable as far as temperature is concerned. So as you increase the PV, the temperature will also increase, and therefore they will fail. So basically through the experimentation we can find out their PV limit, and we can use them for our application.